Welcome, everyone. In this lesson, we're going to be looking at the second derivative test. And the way we use this test, or what we use it for, is to classify our critical numbers. So if we remember, a critical number is a possible location where our function has a local max or a local min. And so, first of all, the critical numbers, those are just the possible locations. Doesn't necessarily mean we do have a max or a min there. And so we always have to do one extra step, and that is classify the critical numbers. And that's where this test is used. We can use this to help us classify our critical numbers. So let's read through it. So let's suppose that we found that x equals c is a critical number for our function. Well, if we were to plug that into our second derivative and get a negative value, what that means is our function has a local max. So if the second derivative is negative there, we have a local max. Now, if we were to plug this critical number in and get a positive value for our second derivative, well, then that tells us our function has a local min. Now, the issue with this second derivative test, it does tend to be a bit quicker than the first derivative test that we've seen. The one issue, though, is it sometimes is inconclusive. And what we mean by that is it doesn't tell us anything about the critical number. So the critical number, it could be a max, it could be a min, or it might not be either. It might be neither. And so we have to do more work in that case. And this inconclusive happens when the second derivative is equal to 0 there. So for this case of inconclusive, it's not the end of the story. What we would do is we would use the first derivative test instead. First derivative test always works for us, but it tends to be a little bit longer because we have to do the sign chart and everything. The second derivative test is a little bit quicker, but sometimes we run into this where it's inconclusive. All right, so let's just talk about these first two. Why do these make sense? And maybe see a way to remember what the second derivative test actually says. So let's suppose that x equals c. It's a point on our curve where it's a critical number. So when the first derivative is equal to 0, they're equal to 0 there, that's what we're taking to be a critical number. And when the first derivative is 0, that means we have a horizontal tangent line. Okay. So if our second derivative is, let's suppose that it's negative. So let's say that we plug our critical number into the second derivative and we get a negative. Well, when the second derivative is negative, that means concave down. And so there's really only one way our graph can look if we know that it has a horizontal tangent and it's concave down all at this critical point. It has to look something like this. It's the only option. Critical number means it flattens out. Concave down means it has this sort of shape. And so if we kind of draw in what this concave down is telling us, it looks like we have a local max, and that's precisely what the second derivative test tells us. If the second derivative is negative, then we have a local max. So this is another one of those cases where it helps to just kind of draw in just quickly what the sketch of the graph is going to look like. So in this case, we end up with a local max. Now in the other case, let's suppose that we had our critical number, x equals c. And again, it's a critical number, so the first derivative is 0 there. So that means we have a horizontal tangent line. And let's say we were to take this critical number and plug it into the original, into the second derivative. And let's say we got a positive value when we did that. Well, positive means concave up. And so there's really only one way our graph can have flatten out, which our first derivative is telling us it's got to flatten out, and be concave up. There's really only one way it can look. And that's this sort of thing. So right around this critical number, this is what our function's going to look like. It's going to have this concave up shape, but it has to flatten out right at x equals c. And so if we kind of draw what the graph is going to look like, it looks like we have a local min, and that's precisely what this test is telling us. We have a local min at this critical number. So it's going to be helpful when we do the second derivative test to just kind of sketch out what the graph looks like right around the critical number to help you classify that critical number. So let's try it out. Let's try example 4. We're going to find the local max and min points for the function 1/4 x squared minus x plus 2. So that's our function. And to start this one, we want to first find the critical numbers. So when we want to locate where we have a max or a min, that's finding the critical numbers. So the first step is getting f prime. And then the second step will be figuring out where f prime is equal to 0 and then solving for x. So things we've done before. This gets us, doing these two steps, this will get us the critical numbers. All right, so let's get our first derivative. So we differentiate. Derivative of the first term is going to be 1/2 x. And then derivative of the remainder here is going to be minus 1. So there's our first derivative. And then we're going to set this first derivative equal to 0. And we're going to solve that equation for x. And when we do, I would probably add 1 to both sides and then multiply both sides by 2. And so we're going to end up with x equal to 2 as our critical number. So this is our critical number here. And again, we don't know what's going on at this critical number. It could be a max, it could be a min, or it could be neither. And so that's why we need one of these tests to help us classify what's going on at this critical number. And so once we have our critical number, then the next step is we got to classify them. And this is where we could either use the first derivative test or the second derivative test. So whenever we do this classify step, we have a choice. So we have a choice here. We could do the first derivative test. And that's where we do our sign chart and we figure out the intervals where f is increasing, decreasing. Or we could do the second derivative test. Now, if we're just trying to classify the critical numbers, normally the second derivative test is a bit quicker because we don't have to do the whole sign chart and everything. The issue, as we've said with the second derivative test, sometimes it's inconclusive. So it does tend to be quicker, but sometimes it is inconclusive. And when it's inconclusive, you have to go with the first derivative test. So, those are the two options here. For this one, though, we're going to use the second derivative test. So let's try that out. But we could have equally have done the first derivative test here. All right, so we got to get our second derivative. And when we calculate our second derivative here, go back up to our first derivative, differentiate it again. Derivative of the first term is going to be 1/2. and derivative of that last term is going to be 0. So our second derivative is just 1/2. And when we have our second derivative, what we need to do is we need to evaluate each of our critical numbers. So we're going to take each critical number that we have and plug it into this formula for our second derivative. Now, in this example, this is a kind of a more basic function. So this second derivative is just a constant function. So no matter what critical number we were to plug into this, it's always going to give us out 1/2. But the idea here is once you have your formula for the second derivative, you're going to take each of your critical numbers and plug it into this formula. But like I said, this one's just a constant function, so it's always going to give us out that constant. So specifically, when I plug in my critical number of x equals 2, I'm going to get 1/2. And so the way the second derivative test works is we plug in our critical number into our second derivative, and then we just have to interpret the sign of this value. And so in this case, this value here is positive, which means concave up, and it helps to actually draw what the concave up shape looks like. And once we do that, we see that it looks like we're going to have a local min, and that's precisely what we have. So the second derivative test tells us here that we have a local min at x equals 2. So the second derivative test, you take your critical numbers, you plug them into the second derivative, you look at the sign of what you get, and you know, when you think about the sign of f double prime, think about how that relates to concave up or concave down. Draw in the shape and see what you have. Is it a min or is it a max? And so what we found here is that there was one critical number. So if we were going to answer our question, the local min and for a local max, well, because there's only one critical number and we found that it's actually a local min, there's not going to be a local max for our function. So local max point, there isn't going to be any. And for our local min point, we know it's happening at x equals 2. We have a minimum there, but to actually get the point, we need our y coordinate. So if I were to take the x value, which was 2, and plug it back into the original function, I'm going to get 1 minus 2 plus 2. So I get 1 for the y value there. And again, so to get the y coordinate for your minimum point or your maximum point, you just take your x value and you plug it into the original function. So a lot of different functions floating around. First derivative, we use that to get our critical numbers. Second derivative, we're using that to classify. And the original function, that's what we're using to actually get the y coordinate for our point. All right. So we're going to try another example in class. So we'll see you then. Bye-bye.